So, in today's session we will continue our discussion on the influence of superplasticizers on early age behavior of concrete. Primarily we will take a look at what aspects affect the compatibility between cement and superplasticizer. Now of course, again the sections are the same in the textbook, but let us look at what we learned in the last class. We talked about what type of surface charges are present in cement as a result of the processing, that is grinding primarily, and how that affects the overall adsorption of chemical admixtures on the surface. As we discussed, chemical admixtures are long chain polymers. The long chain gets adsorbed onto the surface of the cement particles, and depending upon the nature of the polymer, either a surface charge is imparted to the cement particle which causes electrostatic repulsion. Alternatively, the bulky side chains that are present in these superplasticizer molecules prevent the coalescing of cement particles, and that leads to long term maintenance of the workability. Okay. So, that is called steric hindrance, right. And towards the end of the last chapter, we talked about what would be the impact of superplasticizers on cost. And one very important lesson that we ought to learn is that it is not the material cost that is important, but it is the cost of producing concrete of a given quality, right. The cost should be calculated based on attaining the right characteristics in concrete. It is not just a question of choosing something cheaper or something more expensive. It is how they actually impact the properties of concrete that is important. Right, we have been talking on and off about compatibility, right. So, we are obviously dealing with a system that has several different chemical species. There could be complex interactions between these chemicals depending upon the composition of the chemical, the type of processing that each chemical undergoes, right, and the type of environment in which actually you are applying this material in concrete, right. Cement is also a chemical obviously, right. It has got a chemical composition that often dictates the kind of behavior that cement exhibits. Superplasticizer is an organic chemical mostly. Of course, there are some inorganic chemicals also which we will talk about later. Of course, inorganic chemicals are not superplasticizers. All superplasticizers are organic, water soluble organic chemicals. So, when these chemical species are present together in the mixture, there can be instances when you do not get the kind of performance that you desire, right. So, this is what we call as incompatibility. We are not really getting the right kind of performance from the concrete. So, it is a lack of expected level of performance when a given combination of cement and superplasticizer is used. Okay. Now, what are these indicators of poor performance? Slump retention could be a major indicator. In today's world, we want the slump to be retained for a much longer period of time, and that retention of slump becomes quite critical to the way that concreting operations are carried out on site. So, retention of slump, lack of retention is an incompatibility problem. When you retain the slump as expected, then it is a compatible combination, right. Retardation, another example, you have excessive retardation that is happening because of some chemical interactions which does not permit a normal hydration to take place. Then you have bleeding or segregation. In some cases, the water becomes so freed up that it simply rises. Now, water is going to rise in concrete because it is the lightest ingredient, right. It has got the lowest specific gravity amongst all concrete ingredients. So, in a mixture where you have dissimilar weights, obviously the lowest weight has to come on top. You have to decide or design your concrete mixture appropriately to avoid this effect, and this effect could be exacerbated when you have a chemical admixture in the mix. Okay. Low early strengths, another issue. We often design concretes to obtain high early strengths. We want to open up the structure early. We want to carry out the work in a fast track manner and for that attainment of early strengths is very important. So, when you do not get early strength, that is basically a sign of something wrong in the chemical system. So, we have talked about some of these aspects, but let us take an entire look at the factors that can affect compatibility of the cement and superplasticizer. Of course, the type of superplasticizer, whether it is a sulfonate or a polycarboxylate, all of that could have an effect on the compatibility, that is one thing. The composition and physical properties of the cement and the additive materials. These days, concrete is not just plain cement. We often have additives, mineral additives, right, which could have some effect on the overall composition of the cementitious blend, right. And then you have other aspects other than chemistry, like the mixture proportioning of the concrete, how much cement you have, how much water you have, batching and mixing of concrete ingredients, the order in which we put in, like in the last class we discussed that to improve the effectiveness of sulfonated naphthalene formaldehyde, you may want to add it slightly after the water has already come in contact with the cement, right. So, such strategies need to be worked out very clearly to make the concrete produce the right blend of properties. Okay. So, just to put this in a nutshell, if you look at the cement and filler, of course, you know that cement is composed of all of these 4 major compounds. It has got other minor oxides including free lime, sometimes free calcium oxide, right, and it's also got what is the most critical component, the alkali sulfates, sodium sulfate, potassium sulfate and the likes. Okay. Again, these are sulfates and these are highly soluble sulfates. So, you have to take that into account also while deciding on your early age chemical constituent of your pore solution. You then have the superplasticizer. We discussed that in the formulation of the superplasticizer, you want to have a particular chain length which is appropriate, right. You do not want too short a chain length, or maybe too long a chain length is not really worth the effort of going through, right. So, you have high molecular weight chains and low molecular weight chains within the superplasticizer. You may have sulfonate, or you may have other functional groups that are actually associated with the superplasticizer. All of these will have an influence on the way that it interacts with a particular cement. And interestingly, the calcium sulfate that you add to the cement can have a major influence on the way that your system behaves. So, you have gypsum, which is calcium sulfate dihydrate, 2 molecules of water associated with gypsum. Then you have hemihydrate, that is calcium sulfate half H2O. What do we otherwise call this as? POP or plaster of Paris, right. If you further dry this, you get anhydrite, okay, synthetic calcium sulfate, that is what you get if you further dry the plaster of Paris. You may also get natural anhydrite, that means calcium sulfate which is naturally found, that is another possibility. It turns out that when you use one or the other of these sulfate species in cement, the rate at which the sulfate becomes available for reaction can vary. Okay. The solubility of the sulfate is different. As you move from gypsum to hemihydrate, or rather synthetic hemihydrate or plaster of Paris, to synthetic calcium sulfate, your solubility increases. As you go from gypsum to hemihydrate to synthetic calcium sulfate, your solubility goes up. That means the sulfate is available faster in solution to react with C3A to lead to a normal setting process. Okay. Now, you do not want sulfate to come in too early, you do not want a quick set unless the condition really demands it, right. You want a controlled set. So, generally what you will see is in most cements there will be a judicious blend of the different types of sulfates. Now, what happens is when you grind the cement, the heat generated because of grinding, if it is excessive, it can also have a tendency to convert gypsum into other hydrated forms of calcium sulfate, but you want some sort of a combination of these. Okay. Now, it turns out if you use natural anhydride, naturally occurring calcium sulfate, the solubility is very low, it is even lower than that of gypsum. Interestingly, synthetic anhydride can have high solubility, natural anhydride has a low solubility. So, when you start using these systems in your cement, you need to be very careful as to what rate they are actually coming in. We will touch upon this again later. So, the important aspects that really affect compatibility, and if you want to break down chemically and physically, C3A is obviously very important because that is the one which participates in the early part of the reaction. And it turns out more than C3A, it is the calcium aluminate to calcium sulfate ratio or sulfate ratio, not calcium sulfate, because the extent to which sulfate is available is governed by the solubility of the calcium sulfate. The alkali content can also affect the compatibility, right. We'll take a look at how this happens, and fineness of the cement. Why should fineness of cement affect compatibility? The finer the cement, more the surface area, so there will be greater adsorption. So your admixture effectiveness will be good in the beginning, but it may get lost quite quickly, just like the effect of temperature, right. So we talked briefly about this previously, that the sulfonate that is available from the SNF or lignosulfonate may have a tendency to start getting attracted to the C3A sites, okay, right. So it's competing with the sulfate from the gypsum, and this competition can produce a very contradictory effect, right. So your sulfonate from the admixture, when it's going and attracting to the surface of C3A, it's preventing the reaction of gypsum with C3A, but at the same time the effectiveness of the admixture is also getting lost. So you are losing the admixture quickly, you are losing your slump, but you are also getting retarded set because your C3A is not available to react with the gypsum anymore, okay. So contradictory effects, we do not expect two of them to be together, but yes, that happens in this case, okay. Now interestingly, SNF can also inhibit gypsum nucleation. Now what do I mean by that? In some mixes you may have seen that when you start mixing the, when you put all the ingredients in the concrete mixer and start mixing, there is some stiffening that happens in the mix, but when you continue to mix, the stiffening basically breaks down, it does not stiffen that much. We call this phenomenon as false set. Now why is this false set happening? It is happening because if there are other forms of gypsum, right, when they immediately come in contact with water, they convert back to gypsum, okay. When you use gypsum boards, how are gypsum boards prepared? We use plaster of Paris, right, with fibers or with meshes, and this plaster of Paris converts to gypsum, right. So the hardening or stiffening happens when gypsum is formed. Similarly, in a concrete mixture, if the cement has too much of this anhydrite or hemihydrate, it will convert to gypsum as soon as it meets the water. So that is early stiffening, but that can be simply broken by continuing to mix further. That is why we call it false set, okay. But if an admixture is present like SNF, it is going to prevent that false set because it inhibits gypsum nucleation. It does not allow gypsum to nucleate, to form as a crystal, which leads to the stiffening. Interestingly, the form of the C3A, we talked briefly about this in the overview of cement chemistry, that the compounds that are present in cement, the silicates and aluminates, are crystalline compounds and they may have different polymorphs. So type of polymorph can also affect the rate at which C3A becomes soluble, okay. So cubic C3A is less reactive, whereas orthogonal C3A is much more reactive. So solubility of gypsum increases, that is the other reason, from dihydrate, hemihydrate to anhydrite. So as I said, natural anhydrite has very low solubility. So C3A crystal form affects the rate at which it dissolves. Sulfate availability is determined by the type of gypsum that is present in your system, okay. Now just to take a step backwards, in cement chemistry all the reactions happen because the ingredients of cement start dissolving in the water around and recombining to form the hydrated phases, okay. So obviously the dissolution of the cement compounds is a very important step, right. So anything that prevents a dissolution will retard, anything that accelerates a dissolution or speeds up the dissolution will accelerate, okay. So here what is actually happening is the inherent solubility or reactivity of the material is responsible for its availability in solution to do the reaction. So C3A in one form is more reactive than C3A in another form. So if you take a look at this book, Mehta and Montero, they have this very interesting table which consists of the first three columns, okay. They talk about normal hydration process of cement. They talk about the fact that, okay, if C3A is present in one form which is more reactive, one form which is less reactive, combined with sulfate that is available very quickly or not at all available or very slowly available, what happens in a normal hydration process. What I have done is I have introduced a fourth column to see what happens in the presence of a sulfonated naphthenic formaldehyde. So, let us take a look at these in close detail. So, here reactivity of C3A is low, that means it is in the cubic form, it becomes available slowly. You have sulfate possibly in the gypsum form, where solubility is a little bit low as compared to anhydrite or hemihydrate. So, in this case you get what is known as a normal set, but the setting time is between 2 to 4 hours. So, slightly more, but still it sets in normal set. Okay. What is the set which is retarded, which is not normal? As per the code, ten hours, no? 10 hours is the limit placed on initial setting time. Concrete cement should set within 10 hours. So, here you have 2 to 4 hours, it is still a normal set. Okay. When both are high, that means C3A is very reactive and sulfate is also available very fast, you get a normal set. But then the normal set here is 1 to 2 hours, it is less than the previous one, because your initial reactions between the sulfate and the aluminate to form sulfo-aluminates like ettringite, that happens quickly. Okay. So, what happens when in such cases which are seemingly normal for normal concrete, what happens in the presence of SNF? In the first case, SNF does not affect much the overall setting time. Why? Why would not the setting time not be much affected with the help of SNF, in the presence of SNF? C3 is less reactive, so okay, we may not lose the sulfates from the SNF very quickly to the C3A, correct. So, effectiveness of the admixture will be maintained. At the same time, there is sulfate from the gypsum or gypsum sources that could still attract to this or react with the C3A in a normal fashion. So, SNF may not have a major influence there, right. But when the C3A is highly reactive in the second case, in such a case the SNF will now start getting attracted to the high reactivity C3A. Okay. Now, in this case you want to avoid this from happening, that is the reason you go for a delayed addition. You add SNF later, so that this reaction can happen first and then the SNF comes into play. Okay. So, it is very important to understand your system from the perspective of the cement composition and then realize in what stage you need to have this delayed addition made possible. But more interestingly, when C3A is responsible or very highly soluble, but sulfate ion availability is low, what is going to happen? Some of your C3 is available to directly react with water. Okay, it may form a quick set, but at the same time your admixture effectiveness is going to go, because it is getting attracted to the highly soluble C3A and it is causing some slump loss. Well, why should the presence of SNF convert it from a quick set to a normal set? Why? Why do I say that setting becomes normal in this case? Because now your sulfate is not combining with the C3A very early, just like what is happening in a normal case without the SNF, right. It is combining with the C3A in a manner which is similar to the first case, because the admixture went and adsorbed itself onto the C3A, it is not available for reaction immediately. So, it is slowly available for reaction. So, in other words, the presence of the SNF makes this high into low reactivity and converts into a normal setting time. So, from quick set you get a normal set, but you also get slump loss because your effectiveness of the admixture goes down. Of course, when C3A is high and availability of sulfate is nil, that means no gypsum is added in the system, you get flash setting. Now, There is no point in analyzing this because it is not going to happen. We do not really have a system like this in any case. So, there is no need to mix SNF in a system where you know that there is no gypsum added, right. Now, what about the other way? C3A availability is low or reactivity is low, but sulfate is very highly available. That means you have other forms of sulfate than gypsum. So, as I said, there will be false set because you have anhydrite and hemihydrate present in your system. As soon as water comes in contact with this gypsum, it starts forming gypsum, right. You continue to mix, break the set, and then what happens is it undergoes normal set. In the presence of SNF, there is no false set. Why? Because you do not get any nucleation of gypsum. Formation of gypsum crystals is not going to happen because SNF will inhibit that. Okay. So, what this goes to show is that the cement composition in the way that the C3A and CaSO4 are present in your system, the addition of your charged superplasticizers, the polymers that have a surface charge, or sulfonated superplasticizers like lignosulfonate or naphthalene sulfonate, they may have an interaction which can change the nature of the initial chemistry. So, you have to look at this carefully. That is the reason why we want to do the compatibility tests in the lab before we start adding the admixture on site to do the concreting. Okay. So, it is important to do this to try and understand this. What about alkalis? Generally, modern cements have opted for higher alkali contents, and this is because we want to accelerate the strength development. In the presence of more alkali, it turns out that our C3S is able to react faster, right. We talked about the fact that C3S is responsible for early strength development. We already have more C3S in the system. If you have a higher alkali content, you end up getting higher strengths. Okay. Now, the form of the alkali is very important. If alkali is present in the form of alkali sulfates which are highly soluble, it can work very positively if you have sulfonated chemicals like SNF. Why is this? Because the sulfate from this alkali can be made available even before the gypsum starts dissolving to really interact with the C3A to start the hydration process, right. Otherwise, the sulfonate from the superplasticizer, which is again highly soluble, will start getting available and have a competitive adsorption with the C3A. Okay. So, alkali sulfate can be added in instances where you have an incompatible combination. Which one of these is incompatible combination? Which one? First one is incompatible? No, right. Second one? Possibly, because you get slump loss, no. So, it is incompatible, right. What about third one? Is it is still incompatible, you get slump loss, right. So, in such cases, having a sulfate source that is highly soluble like an alkali sulfate can help. Okay. But what happens is alkali is present in the solution can lead to acceleration, and that leads to slump loss. So, there is a competitive effect here. The sulfates from the alkalis are helping, but the alkalis themselves, because they accelerate, they lead to slump loss. So, you need to evaluate the situation carefully. Most Indian cements seem to have alkali contents that are fairly on the lower side, about 0.5, 0.6%. How is alkali content represented in cements? As percentage equivalent sodium oxide. Alkalis in cement are represented as percentage equivalent sodium oxide. Why? Because alkalis typically in cement are present in two forms, sodium oxide and potassium oxide. We convert potassium oxide content to an equivalent sodium oxide content by taking a ratio of the molecular weights. Okay. Now, as compared to Indian cements, if you go to Europe or US, their ordinary cements have much higher alkali contents, somewhere close to even 1%. Why do they do this? Because they want their cement performance in terms of strength at early ages, the demand is much more than what our cements actually produce. So, they have higher C3S, higher alkali, higher fineness as compared to Indian cements. Okay. So, maybe I mean, I have not really done an extensive study of the admixtures available in the European and American markets in terms of the compatibility issues. Maybe there the challenge of compatibility could be sometimes greater than what we see here, because our alkaline contents are usually smaller.